We got Oscar, Jessica, Crystal, Kelsey, Mark, and Maggie. Right. Any questions about the homework from yesterday? Or the stuff that's due tonight, stuff we covered yesterday? Okay, so yesterday in class we talked about ways to describe qualitative data. Right? Qualitative data is any type of data that cannot be written in numerical form. Right? So here's an example from the book. This well class, whether it's public, where the aquifer is, and then detect MTBE. All those are qualitative types of data. There was 3 types of graphical methods for qualitative data. The pie chart, the bar graph, and the Pareto diagram, which is basically just a bar graph in descending order, right? The observation that occurs the most is on the very left, and then they go down in occurrence as you move from left to right. All right. Okay. Everybody get the sign-in sheet? Thank you. Right. Okay. So, today in section 2.2, which we'll cover 2.2 and 2.3 today, we are talking about graphical methods for describing quantitative data, data that can be packaged in numerical form. All right? Okay, so recall from section 1.4, which was part of the definition section, right, from chapter 1, that quantitative data sets consist of data that are recorded on a meaningful numerical scale. All right, to describe, summarize, and detect patterns in such data, which is what we do in descriptive statistics, right? We describe, summarize, and detect patterns. We can use 3 graphical methods. So there's 3 graphical methods, just like there was 3 graphical methods in the qualitative data section. The first one is what's called a dot plot, which is really similar to a bar graph. A stem and leaf display, which is probably not something you've seen before, but they're pretty simple to construct. And then finally, something called a histogram. What makes a histogram is, it's a form of a bar chart, but all of our bars are compact together. They're all touching each other. There's no space in between. We remember in our qualitative data, that was one thing that we had to do, right, when we graph things, was we had to separate, right? There had to be a difference between the 2 things. In quantitative, when we deal with numbers, there's not going to be a gap between 2 observations, and we'll see that today. All right? Since most statistical software packages can be used to construct these displays, we'll focus here on the interpretation rather than their construction. Your homework, there'll be some construction. There's actually 3 videos in your homework that shows how to create all 3 of these displays, all right, in StatCrunch. Okay, so for example, the EPA performs extensive tests on all new car models to determine their mileage ratings, right? How many miles per gallon do they get? Suppose that the 100 measurements in Table 2.2, which is on the next page, represents the results of such tests on a certain new car model. how can we summarize this information in this rather large sample? Now, we wouldn't want to take these 100 measurements and do it per car, because what if there's a lot of cars, right? That would be a qualitative data set. So here's a bunch of different miles per gallons for different cars, right? Notice none of them are very low, so these are probably all compact cars, right? Pretty small vehicles, because the mileage ratings are all pretty high, right? I don't even see one in the 20s as I glance at it. But looking at this chart, it's practically impossible to determine which one occurs the most. What's the most prevalent mileage right here? Well, we have to get in and actually do a graphical interpretation of it to try and detect a pattern, right? That's what we do in descriptive statistics. A visual inspection of the data indicates some obvious facts. For example, most of the mileages are in the 30s, some are in the 40s, none are in the 20s, I notice. But it is difficult to do anything else, right? We can't really create any other pattern, right? There's really nothing to see. A question you might ask yourself is, what is the average mile per gallon amongst all these data points, amongst all these observations? All right, so a dot plot, a Minitab dot plot for the 100 EPA mileage ratings is shown in figure 2.8. So all they do here is they create a scale and they put a dot for each occurrence, all right? So each observation gets a dot. If you count the number of dots in this dot plot, it's going to be 100, all right? And as we can see here, the number that occurs the most seems to be a mileage a little bit below 37, up above 35, something right in the 37 range is what it looks like is about the average mile per gallon as I look at this dot plot. Right? So really it's just a bar chart in a sense that we're just putting the frequency of each occurrence. Notice there's nothing on the y-axis here. Right? It doesn't say what the frequency is of these. We can actually go in and count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there was 15 occurrences of that data point. Right? Notice up here it says, when data values repeat, the dots are placed above one another, forming a pile at that particular numerical location. As you can see, this dot plot verifies that almost all the mileage ratings are in the 30s, and actually most of them are right in between, 36 to 38 miles per gallon is basically where the bulk of them live, right, and where they are. So that's simply what a dot plot is. You take each observation and put a dot. Now you'll notice if you had 1,000 observations, your dot plot would become more difficult to create, and then you would start to lose clarity of what's going on, right? So dot plots are only used in certain situations where your n value is relatively small, okay? So there's another type of display we can use to plot all of this data that is known as a stem and leaf display. In a stem and leaf display, what we call the stem is the first number, and the leaf is the preceding numbers. Okay, so let's take a look at it. Okay, so it says another graphical representation of the same data. So it's the exact same data points. A stem and leaf display is shown in figure 2.9. In this display, the stem is the portion of the measurement to the left of the decimal point. So there'll be two values in the stem in this particular case. Your stem might have 3 values, your stem might only have 1 value. It depends on what observations you're looking at. Okay? So what we're going to do is we're going to take the first 2 values and let that be a stem. So we'll write 35 and we'll look at everywhere that 35 occurs and then put the leaf as the value occurring after the decimal point. And you always put it in ascending order. You always put your leaves from 0 to 9. Okay? So let's take a look at it. This is all occurring on page 38 in your textbook. It's on the next page. Okay. In figure 2.9, the stems for the data set are listed in the second column. Right? So over here is the frequency of the stem. All right? How many of them are there? Okay? And finally, let's keep reading. Then the leaf for each observation is listed to the right. Okay? In the row of the display corresponding to the observation stem. For example, leaf 3 of the first observation 36.3 in table 2.2 appears in the row corresponding to the stem 36. Right, so right here. Stem 36. And there's all the different observations at that point. Right? Similarly, the leaf 7 for the second observation, 32.7 in table 2.2, appears in the row corresponding to the stem 32, while the leaf 5 for the third observation, 40.5, appears in the row corresponding to the stem 40. All right, so right here's the stem 40, and then here's each of the occurrences. So 40.0, 40.1, 40.2, 40.3. Notice whenever they repeat, you just write it down again. You guys see that? All right. The stems and leaves for these first three observations are highlighted in figure 2.9. Typically, the leaves in each row are ordered as shown in the mini-tab stem and leaf display. Notice the leaves are always in ascending order. They're always from smallest to biggest. All right. And then it says our leaf unit here is in tenths. All right. So, 30 only occurs one time, 30.0. There's not a 30.1, there's not a 30.2, there's not a 30.3. And if we go back and look at the data set, we'll see that. Let's go in and find our 30.0. There's a cool little pointer in here. Where's it at? You guys see it? Oh, right here. So there's our 30.0. Do you see any other data points that have a 30 point something? No, right? They don't occur. There's only one. So that's our 30.0. So really, to create your stem and leaf display, you would really want to write all these numbers down in ascending order, right? So you'd want to rewrite all 100 of these observations. Or you can go through at a case by case, right? Do 36.3, write each down in a stem and leaf, and then rearrange the ascending order of the leaves. Right? So start off with 36, put 0.3, go up 32.7, and go on like that, and then reorder your leaves. Okay, so the stem always goes from smallest to biggest, from top to bottom, and then the leaves go from smallest to biggest as you read from left to right. Okay? So in your homework, you're asked to read and interpret some stem and leaf displays. Okay? So it says, the stem and leaf display presents another compact picture of the data set. You can see at a glance that the 100 mileage ratings were distributed between 30.0 and 44.9. Right? That's the total number. So the smallest miles per gallon was 30.0. The best miles per gallon was 44.9. With the most of them falling in stem rows 35 to 39. The 6 leaves in stem row 34 indicate that 6 of the 100 readings were at least 34.0, but less than 35. Similarly, the 11 leaves in stem row 35 indicate that 11 of the 100 readings were at least 35.0. So let's interpret this left-hand column over here. So you notice it counts up from 1 to 2 to 6 to 12 to 18. What that is a cumulative observation. All right, so notice at 30.0 there's 1. And then here, so there's 1 here and 2 here. So total, up to that point, there's 2 observations. That's what that's saying. Notice the third number is 6. Up to that point, so from that point backward, there are 6 observations, right? There's 1 at 30.0, 1 at 31.8, and then there's 4 observations here. So that makes a total of 6. That's where that number is coming from, all right? So that's the frequency. And then it keeps building up to right here, 18, and notice it says 11 right here in the book. Okay. Similarly, the 11 leaves in stem row 35 indicate that 11 of the 100 readings were at least 35. You notice the difference between 18 and 29 is 11, right? So from stem row 34 to stem row 35, we put 11 more observations in there. This one in the middle just counts the total number, right? So it kind of goes from both directions. We see that? This could be written in another manner where you just simply keep counting up all the observations and this number gets bigger, right? Let's read what it says here. But less than 36. Only 5 cars had readings equal to 41 or larger, and only one was as low as 30. So notice in this case they're counting up going this direction, right? One here. There wasn't a mileage rating at 43. You see that? Because it would have been 43.0, right, if it would have been exactly 43. So there was not an occurrence of a miles per gallon at 43, right? That's why there's not a leaf to that stem. But you can't skip, so that's why they had to include this 43 right here. If there would have been a mileage at 50, they would have had to put 45, 46, 47 with nothing over in the leaf, and then get down to 50 and put 50.0. Right, you guys kind of see what's going on there? The definition of the stem and leaf for a data set can be modified to alter the graphical interpretation. For example, suppose we had defined the stem and leaf as the 10 digits for, this is talking about John Tukey, if you're interested to read about that, for the gas mileage rating rather than the ones in tens digits. With this definition, the stem and leaves corresponding to the measurements 36.3 and 32.7 would be as follows. So notice here they let the stem be the first number and the leaf is the second number, and they basically ignore the decimal. Okay? So it's just a different way to display this information. Note that the decimal portion of the numbers has been dropped because it's not a very significant value. When a car is getting 36 miles per gallon, another 0.2 of a gallon really isn't that significant when you compare it to 36 miles per gallon. So that's why they tend to drop it in this case. Now, if we're talking about something at a microscopic level, right, or something very small where a decimal value is a lot in a relative sense, right, if we're talking about angstroms of an atom or something like that, then you would want to include all the decimal values. Okay? So it really just depends on the situation. If you look at the data, you'll see why we didn't define the stem this way. All the mileage measurements fall into the 30s and 40s. So all the leaves would fall into just 2 stem rows in this display. Right? It would just be 30, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then in the 40s, and that's it. There would just be 2 rows. So that's why we don't define it this way. The resulting picture would not be nearly as informative as figure 2.9. All right. What I want to do now is have you guys create a dot plot and a stem and leaf display. All right. So I have an example written right here. Zoom that in. So get out a piece of paper. Okay. 10 people were asked their age, and the results are provided below. Use the data set to answer the following parts. All right. Construct a dot plot by hand representing the above data set. Be sure to label your horizontal axis. Now, something I want to mention in the dot plot is what type of order is our horizontal axis in. All right, let me jump back to the computer real quick. Is this in order? Or does it skip around and show 37 and then 35 and then 31 and then 42? Notice how it's in order right there, right? It goes from smallest to biggest as we read left to right. So these values on the page aren't in ascending order, right? They don't go from smallest to biggest. So that might be the first thing you want to do here, is rearrange these values so they are ordered from smallest to biggest. All right? So I see the smallest value here is 43. I'll give you a minute to try those. So create a dot plot and then construct a stem and leaf display. Your stem will be the first value, your leaf will be the second value. All right? First we want to rearrange it into ascending order, 43, 44, bless you. So what are you doing on this? So remember what we had to do in that gas mileage stem and leaf display for that one value that didn't show up. And I mentioned that when we were looking at it. There's no way I could. This Elmo is a little bit older. It doesn't really have the same type of setup as the other ones. That's a little brighter, isn't it? I'm going to give you guys another couple minutes for this. All right, so I'll go ahead and slide this over and you can look at our dot plot here. See if you have the same thing as I do. So notice here I'm not really concerned with scale, right? Look how many numbers I skipped right there from 59 to 71. The scale isn't as important as identifying each value. Anybody not quite have what I have there? Have questions about it?
I put mine as like 40, 45, 50, 55.
And that's, yeah.
Is that
That's,
fine?
yeah, no, that's fine. Yeah. Yeah, as long as your dots occur in the right place. Now, when you do it that way, you have to pay attention to scaling a lot more, right? So something that you know, we do as mathematicians when we skip some space is say to erase right here and put a little heartbeat-looking symbol. That means we've skipped a little bit, right? So that shows that there's a break in the graph right there. And a lot of times, I mean, this is a very small sample, right? This is a very small data set. So it makes sense to do it by point. But when you get a little bit bigger data set, you definitely want to do it the way that you're talking, to actually create a scale and then put the dots. Just like the miles per gallon one was, right? The miles per gallon didn't have each mile per gallon written down here. What's important is that you get the data across, right? You interpret the data correctly. Okay, so there's our dot plot. And down here, these were ages. We don't know what it was in, right? 43 is the youngest, 85 is the oldest. I mean, this could be a lot of different things. This could be the ages of people at McDonald's at 9 o'clock in the morning, right? Maybe after school starts and they're all in there drinking coffee. All right. Okay. Now let's look at our stem and leaf display. Here we go. All right. So notice I put stem and leaf. And you might see a line drawn down right there to separate the stem and leaf in some places. Doesn't necessarily have to be there. That's just another interpretation of it. But notice that you do have to include the 6 here, right? You can't have the skip. But notice there's no second value for the 6. So that means there was no occurrence of people in the age of 60, right? 60, 61, 62, all the way up to 69. So we can see which decade appears the most. That would be the 50-year-olds. And the age 58 actually appears twice. All right? Any questions about that? Now, what if I was graphing temperatures on the sun, right? And these numbers were huge. I mean, in the millions. Basically, you'd have to write the data set down and really see where they differentiate each other. You know, because maybe they're all 10 million degrees and then the 300,000s change. You probably want to let the stem be the 10 for the million and then let the leaf be the next value after the 10 million and 700,000 or 10 million and 800,000. All right? But notice in the leaf, right, there can only be one value in each of these. So 43, 44, 46. All right, this isn't a 3-digit number. These are just 2-digit numbers. All right. The stem can be 2-digit, which we already seen in the miles per gallon problem, but the leaf can only be 1 digit. Okay? Can't be 2 digits. Ready? Nothing too mind-blowing about those 2 displays. The next one I definitely like more, though. It really explains, it really has a way of showing the data a little bit better, and then it kind of creates a shape of the distribution. We're going to talk about shapes of distributions a lot in this course. Right? So the histogram really helps us create that. Okay. An SPS histogram, let me move this over and make it a little bit bigger. Okay. An SPS histogram for the 100 EPA mileage readings given in Table 2.2 is shown in this next figure. All right? Now this, up to this point, our dot plot just had the x-axis. We weren't labeling, or the horizontal axis, I'm going to call it, not the x-axis. The horizontal axis was labeled, but there's nothing for a vertical axis here. Right? In the stem and leaf, there's not even really a vertical or horizontal axis. The histogram, we kind of get back to think about kind of the bar chart from the qualitative data. A histogram is a lot like a bar chart. The difference is the histogram, our bars are compacted together. All right? There's no space in between. And we'll see why. All right? The horizontal axis of the figure, which gives the miles per gallon for a given automobile, is divided into class intervals. Now, doesn't that sound a lot like what we did for the qualitative distributions, right? We separated them up into classes. Right? Commencing, which means beginning, right, with the interval from 30 to 31 and proceeding in intervals of equal size to 44, 45. So notice the intervals are of 1 mile per gallon, but anything that's 30 or 31 miles per gallon falls within that class interval. All right? Now, how you determine how big to make these class intervals depends on how big your sample size is. And we'll see, there's a nice rule of thumb for how big to make these class intervals. Okay? The vertical axis gives the number or frequency of the 100 readings. So we could very easily take the histogram from a frequency histogram to a relative frequency histogram, right? Especially when there's 100 readings. Because if something appears 10 times, then its relative frequency would be 0.10, right? Because you just divide it by 100. So whenever you're dealing with 100 readings, it's really simple to go from frequency to relative frequency. Right? 100 is a nice round number. It appears that about 21 of the 100 cars, or 21%, so the frequency and the relative frequency, which this is the percentage, right, which is just the relative frequency with the decimal moved over twice, is the same value. Right? If we had 50 cars, then if there was 21 of 50, then this would be 42%, right? So when you have 100 observations, this stuff is a lot easier to interpret in that sense. So 21% attain a mileage between 37 and 38 miles per gallon. This class interval contains the highest frequency, and the intervals tend to contain a smaller number of measurements as the mileages get smaller or larger. So in the middle, we're going to have the bar be the highest. As we go smaller or bigger, the bars start to get a little bit smaller. Okay? Histograms can be used to display either the frequency or relative frequency of the measurements falling into the class intervals. The class intervals, frequency, and relative frequencies for the EPA mileage chart, for the EPA mileage data, are shown in the table. All right? So here it is. Here is a histogram. Now you notice there's no space in between. It starts at 30, goes to 31. Then from 31 to 32. Then from 32 to 33. Now what you'll notice here is there was no observations at 43, right? You guys remember that in that stem and leaf display? So basically the left-hand endpoint, let's look at the stem and leaf. Okay. Notice at 43 there was no observations. At 42 there was 1. At 44 there was 9. At 30 and 31 there was, or not 9. 44 there was only 1. 44.9. So in these 4 miles per gallons, at 30, 31, 42, and 44, there was only 1 observation in each category, right, in each class interval. So as we look at our histogram, we see that the left-hand value is, the left-hand value is where we stick our miles per gallon. So any miles per gallon from 30 all the way up to 30.9 would occur in here. Then from 31.0 to 31.9 would occur in here. And from 32 to 32.9 would occur in here. Notice as we look in the chart, it says that a miles per gallon in the range of 32 to 32.9 looks like there's 4 observations, right? The frequency is 4. So if we go back to that stem and leaf display, and I go and look at 32, there should be 4 leaves. And lo and behold, there is at 32. There's 1, 2, 3, 4. So there's 4 observations of a miles per gallon from 32.0 to 32.9. All right? Notice if I took this stem and leaf display, and if I could pick it up off the computer and kind of turn it, right? If I could kind of turn it on its side, this shape is relatively the same shape, right? If I took it and kind of spun it this way, it's basically the same shape as the histogram. All right, does everybody see that? So if I took that stem and leaf display and spun it this direction, so we can see here that between 36 and 38 miles per gallon is where most of the observations occur. Well, a lot of them. I shouldn't say most because it's not quite 50. But there's more observations between 36 and 38 than in any other 2 mile per gallon interval. Now you'll notice the shape of this graph starts off really small, then it gets really big in the center, and then it drops back off as we get big. That's a very specific shape in statistics. Anybody know what that shape is starting to become? There's a special name for it. You probably heard it before. I know if you took 106, you've heard it. So if I was going to take the left-hand endpoint of each of these rectangles and kind of create a nice line, go up and then start to come back down. What's a word that's synonymous with regular? Symmetrical, or it starts with an N. Mound, that's another one. Normal, the normal distribution. Yeah, have you ever heard, outliers, right? The term outliers means they're far away from the center. These things are not quite outliers, but they're starting to become outliers. This graph has what's called a normal distribution. A lot of things in life, well, it's approximately normal. We can't say it's exactly normal. And that really only talks about when we get to continuous values, which we haven't even discussed yet. But I want you guys to start thinking about the shape of this thing. There's a lot of things in life that occur in this shape. Think about heights of individuals, right? If I took the height of, say, 1,000 males, age 25, most of them would be right here, about 5'10", right? 5'9", then less and less would be shorter than that, and less would be taller than that. So this normal distribution occurs all the time in the real world. IQ, weight, a lot of different things. I mean, we'll see so many examples of the normal distribution, you'll eventually get sick of it. I mean, I hope not, but maybe you will. All right, so that's what I want you to kind of start looking at. Because there's a lot of really neat things we can do with the normal distribution. That's where we start talking about standard deviations and plus or minus 1 standard deviation. That's how we finally get to confidence intervals, right? How big do I need to go out from my center here to where I get most of the data, right? What's the interval I need to get to? That's the kind of stuff we're leading into, right? So this type of shape is very important. Now, car miles per gallon, I mean, this is a very specific type of car, right? They're probably compact cars here. There's obviously no pickups here. There's no big V8 cars here, right? Because their miles per gallon is way down here, right? Down in the 15 or 20 range. So this is probably normal if you go to Europe, right? Most of the cars there get this kind of mileage, right? They're all pretty small. None of them are very big. This is definitely not typical of, say, a parking lot here in Portales, right? This thing would be, the distribution might be like this, but these numbers would probably range from about 12 up to about 35, right? More than likely. Most people would be right about that 25, 30 range. All right? Let's read what it says right here. SPS, like many software packages, will classify an observation that falls on the borderline of a class interval into the next highest interval. For example, the gas mileage of 37.0, which falls directly on the border, right? 37.0 gets classified into the higher interval, right? The frequencies in table 2.3 reflect this convention. Right, so that is a frequency histogram. Now, what's something I could do to make this a relative frequency histogram? basically, what would I have to do here since all of these, how many total observations are there? 100. I need to take each one of these values and divide it by 100, right? Or just move the decimal over twice. So if I made this instead of 5, if I called it 0.05, call this 0.1, 0.15, 0.2, I have created a relative frequency histogram. All right? Or since there's 100 observations, being frequency or relative frequency, it isn't much of a difference. But what if there was 38 observations? Then a relative frequency histogram would really tell you more. Right? Any questions on this? You know, you might be thinking, what if there was a mile per gallon 38.01? Where would that get classified into? What if I said 38.01? Would it go into the 37 column? 39. So let's just consider that right there. Would this observation go into the left-hand bar or the right-hand bar? The right-hand bar. Exactly. It would definitely go in there. Okay. And then here's a breakdown of the histogram. Notice when I sum together the relative frequencies, I get the number 1, right? Which is very important. If you don't get to 1, then you've missed some observations somewhere. Something isn't in your graph that needs to be there, right? It can't be more than 1. It can't be less than 1. It has to be exactly 1. Now, as we'll see, you know, when you get a really big size, you know, maybe if this was 990 observations, and we only want to do our relative frequency out to 2 decimal places, there might be a round-off issue when we get to 1.0. But that's something you address with each situation, right? Okay? Pretty interesting stuff here. So if we just take these 4 class intervals, what is it, 41, 52, 62, right? So almost 2/3 of all the observations fall within 34 to 39 miles per gallon. It's a pretty small window when you consider it ranges from 30 to 45. There's a special word for that too. When I take my smallest value and go all the way up to my biggest value, the difference between those two things, there's a special word for that we'll see. All right? Okay. The cars obtain a mileage rating. Oh, what is this? Let me go back in. Okay. By summing the relative frequencies in the intervals 35, 36, 37, 37, 38, and 38, 39, you find that 65% of the mileages fall between 35 and 39, which is what I was just talking about. And only 2% of the cars obtained a mileage rating over 42, because that's this one, plus this one, plus this one, which is 0.02, which becomes 2%. Many other summary statements can be made by further examining the histogram and the accompanying summary table. Note that the sum of all class frequencies will always equal the sample size n. Now, what if I erase this? What if I told you the sample size, if the frequency column was gone, and I told you the sample size was 50, and the relative frequency of 36 to 37 was still 0.21, how many occurrences were there? But if the sample size was only 50, that's something you'll have to do on your homework, all right, that we'll think about. So you're given the relative frequency and the n value. So something you can think about with that is convert, say, 0.21 to a percentage. So let's let n equal 50 and the relative frequency of the class say 37, 38 is 0.21. Okay? How many observations and when I say how many, I'm asking what's the frequency. How many observations are there in this class? So that's 50 observations, and the relative frequency was 0.21. So let's think back to our relative frequency formula. So let me go back to section 2.2 and see if we can kind of unwrap that formula. This is something I haven't talked about yet, but it's something you have to do on your homework. Where's that? It's back at the beginning. Right here. Let's look at this formula. So I'm asking for this, right? I'm asking for how many observations. What's the n value for that case? 50. What's the relative frequency? 0.21. So that implies that I have this. 0.21 equals, my unknown is my frequency, right? When I say how many. So I'm just going to call that x. I can call it y, z, q, r. I'm just going to call it x. X over 50. And this is what I was saying on the first day when you got to have some understanding of simple algebras. How do I solve that for x? Multiply both sides by 50. Which is the reciprocal, right? This is the fraction 1 over 50. The reciprocal of 1 over 50 is 50. So I'm going to multiply both sides by 50. And that implies that x equals, get out your calculator, just to make sure. I mean, this is something you can do in your head, but 50 times 0.21. And what do we get? Now, in this case, I kind of just made this example up. So, of course, there can't be half a car, right? This is just something I kind of pulled off the top of my head. Right? So, yeah, you can't have half a car. So really what you would say here is 11. But what I wanted to get to was solving this equation for the frequency. Okay? This is something you'll have to do on your homework. You'll be given a relative frequency, you'll be given an n value, and you have to determine what the frequency is. Okay? So it uses this formula right here. You can rewrite this formula. So class RF, class frequency equals class frequency over the size of the class. Or the size of the entire data set, not just the class. The size of the class is the class frequency. All right? And you notice another thing about 10.5 is that's 21 divided in half, right? What page was that on? 41. All right, so that is something you'll have to do on your homework. So, in interpreting a histogram, consider two important facts. First, the proportion of the total area under the histogram that falls above a particular interval on the x-axis is equal to the relative frequency of measurements falling into that interval. Now, that sentence you could read 3 or 4 times and not really digest the whole thing, right? There's a lot going on in that sentence. The proportion of total area under the histogram. I mean, that's bringing in a lot of different things in mathematics. Area under the curve. I mean, that's the beginning of calculus. You know, that's something we talk about, is the area under the curve. So that's what this is kind of talking about. Now, we're not going to do any calculus on it. Luckily, it's been already done for us, right? That falls above a particular interval on the x-axis is equal to the relative frequency of measurements falling into that interval. For example, the relative frequency for the class interval 3738 in figure 2.10 is 0.2. Consequently, the rectangle above the interval contains 0.2 of the total area under the histogram. Do we get that? So this is, if all the area of the histogram, right, if I said this was 1 square unit, this would be 0.2 units. Right? Is that what it was? No, it was this one. The one that goes to 20. This would be 0.2 units. Right? If I let this be 1 square unit, if I added together all this area, which we could find the area of a rectangle, it's just base times height. Right? So when you start having a smooth curve, then it becomes a little more difficult to find the area. So imagine if I shrunk these classes down. You know, instead of it going from 30.0 to 30.9, I have it from 30.0 to 30.1 and I create a class. 30.1 to 30.2 and I create a class. So I make my intervals smaller and smaller and smaller. Here's what happens to the graph. Notice what's going on here as I get a very large data set. This is starting to look like a curve, isn't it? It's starting to kind of look like a parabola. Not quite, because of the way it goes out at the end. But this looks a heck of a lot more like a curve than this does, right? And that's just because I have a very large data set, so I break it down into more measurement classes. Okay? So you might be asking yourself, how many classes do I need? What if I have a data set with 1,000 observations? How many classes should I make it into? Should it only be 10? Should it only be 5? Should it be 20? Here's some recommendations from the book. All right. Determining the number of classes in a histogram. So the number of observations, fewer than 25. The number of classes should be 5 to 6. Now our miles per gallon problem didn't quite fit into this. It was pretty close. How many classes were there? Let's go and count them. So how many classes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And how many observations were there in this? 100. So does this fall into this chart? We had more than 50 observations. The number of classes should be 15 to 20. So it did. Right? Notice it says 20 is basically the maximum number of classes, even for a data set that's big. That's really big. Right? And these can change depending on the certain situation. Right? But that's kind of a rule of thumb. Some recommendations for selecting the number of intervals in a histogram for smaller data sets are given in the following box. Okay. So let's get to some summaries now. Let's summarize our 3 types of graphs, and then we'll do a histogram activity, and maybe take a break. You guys can go use the restroom real quick, and then we'll get to the next section. Here we go. Summary of graphical descriptive methods for quantitative data. So just in that definition, right, or just in this title, there's 2 or 3 definitions we need to know. We need to know what data is, we need to know what quantitative is, and we need to know what descriptive methods are. Right? Those are all words that came from Chapter 1. The dot plot, the numerical value of each quantitative measurement in the data set, is represented by a dot on a horizontal scale. When data values repeat, you basically just make the dots higher, right? They go vertically. Stem and leaf display, this is on page 43 in your textbook as well. The numerical value of the quantitative variable is partitioned into a stem and a leaf. Remember, the stem can be more than one value, but the leaf can only be one value. Or else it gets very confusing, right? If your leaf is 2 digits over here. It's basically impossible to interpret. The possible stems are listed in order in a column. The leaf for each quantitative measurement in the data set is based in the corresponding stem row. Leaves for observations with the same stem value are listed in increasing order horizontally. So the stem increases from top to bottom, right? It gets bigger in this direction, and the leaf gets bigger in that direction. So on a stem and leaf display, your biggest value will always be down at the bottom right corner. Your smallest value will always be up here at the top left. Just like when you're reading in a page, right? You start at the top left, you end at the bottom right. Okay? Right. The possible numerical values of the quantitative variable are partitioned into class intervals. How do we determine how many class intervals? Well, it depends on the size. Each of which has the same width. That's important, right? All of our class intervals have to have the same width. Right? We couldn't have our miles per gallon, one of them be 2 miles per gallon, then one of them be 1, and then another one be 2. That doesn't make sense. You can't do it that way. They all have to be the same width. Right. The frequency or relative frequency of observations in each class interval is determined. A vertical bar is placed over each class interval with the height of the bar equal to either the frequency or the relative frequency. Okay? All right, so let's do an example here. This example, it goes a little bit further. It's asking you to put together multiple intervals here. Is that a little too bright? I think so. That's definitely not bright enough. Great. There we go. How's that better? Well, that's a little too dark. Okay. So, use the histogram given to answer the following questions. Round your answer to 2 decimal places if needed. So let's look at our chart. Look at the title first. The number of minutes arrived late to class for 105 students. So this is in one class that has 105 students, which there's not very many classes here at Eastern that are that big, right? You go to a big college and most freshman level classes are at least this big, right? At big universities. UNM, New Mexico State, UT, Texas Tech. Which that would be, to me, that would be a little difficult to be in a class with that many people. That's neither here nor there. So this is the number of minutes arrived late to a class for 105 students. Right? I might ask you, how many students were between, so it does have between 0 and 3. So notice it includes the students that weren't late at all. Look, it looks like most students were pretty late for this class, right, as we read it. If we add together all of those observations, does it total 105? Let's add them all together and just see. So let's do 4 plus 16, so that's 20, plus 32, plus 29, plus 18, plus 6. 105. So they're all listed there. This is not a very punctual class as we look at this, right? Okay, first question says, based on the histogram, what proportion of the students arrived between 0 to 6 minutes late to class? Basically, I want to know what is the relative frequency of that. So, first of all, what's the frequency of students that arrived between 0 to 6 minutes late? How many were there? 20, right? That's this bar plus this bar. But it says proportion, so I want to know out of the total. Not the frequency, what's the relative frequency? That's what proportion means, is compared to everyone else. So the answer to part A would be 20 over 105. Which equals what? 0.19, rounded to 2 decimal places. So basically, about 20% or 1 out of 5 students was 0 to 6 minutes late for class. Maybe there was a traffic jam on campus, right? That kind of held them all up. Because they all seem to appear right here in this 6-minute interval is where most of them show up. Right? There's what? 61, which is way more than half, appear between in here. So there must have been some type of snafu out in the parking lot. Right? Maybe there's a fire drill or something in their dorm. Based on the histogram, how many students? Now this says how many. This does not say the proportion. Do we see the difference between those two things? How many is frequency. Proportion is relative frequency, right? So what's the answer to part B? 29. Between 9 and 12 would be 29 students. If I asked you for what proportion of students, it'd be 29 over 105. Okay. Based on the histograph, there's a word I kind of put together there. How many students were between 0 to 9 minutes late or more than 15 minutes late? In mathematics and statistics, the word or means both put together. One or the other or both. So it's this plus that. All right, that's what or means. In English, or usually means this one or the other. It can't be both. In math, it does include both. And we'll see that when we get to Venn diagrams, that or does include both. So first we need to count the number of students that were between 0 to 9 minutes late, and then count the number of students who were more than 15 minutes late. So that's basically this bar plus this bar plus this bar plus this bar. Right? You guys agree with that? So 20 plus 32 is 52 plus 6, 58. What you guys got? If I asked you what is the proportion of students, it would be 58 over 105. Okay? Any questions on this? So what if a student was exactly 9 minutes late? Do they go in this bar, the left bar, or the right bar? The right. It always goes to the right. If it's right on the point, it's always the bar to the right, which is what happened in the miles per gallon example, right? Let's go back and look at that again. What's on the previous page? Right here. Yeah, here. It's down here at the bottom, right? So this answers that question. We'll classify an observation that falls on the borderline of a class interval into the next highest interval, into the interval to the right. Right? Into the next highest interval. For example, the gas mileage of 37.0. Similarly, if you were exactly 9 minutes late, would fall on the border between the class intervals 36, 37. So, and 37, 38 would go in the higher of the two intervals. Now, does this graph I show you, does it follow this rule of thumb down here? Yes or no? How many observations were there in the class, the students late graph? 105. So that's this number, right? More than 50, which means it needs to be divided into 15 to 20. That class it only was divided into 6. So this is just a rule of thumb. It's not set in stone, right? Really, if I was going to create that, I would probably break it down into a minute by minute. 0 to 1 minute, 1 to 2 minutes, 2 to 3 minutes. That's not something we could do based on this data. We don't have enough information to do that. So I would break it down into 18 intervals. Okay? All right, guys, what I want to do is take a small break. Let's do a 5-minute break. So it's 5 after I want to come back at 10:10. We're going to start the next section. All right, so that gives you time to go get a drink, use the restroom, stretch our legs out. And now's a good time to ask questions if you have any. So it gives you some time. But, yeah, do some things. Have you ever
Yeah.
so you can use your spoons or your password. You just use this course. Okay, yeah, same thing. Yeah. Okay. All right, so for this section, have your calculators out, because I'll show you in your calculators where we can do this stuff. Because they have really nice operations for this summation notation. Okay. Now that we've examined some graphical techniques for describing quantitative data sets, so this is just dealing with the numbers again. The summation notation doesn't work for qualitative data sets, all right? It's just quantitative data sets. We turn to numerical methods for accomplishing that objective, all right? Before giving the formulas for calculating numerical descriptive measures, let's look at some shorthand notation that will simplify our calculation instructions, all right? Remember that such notation is used for one reason only: to avoid repeating the same verbal descriptions over and over. If you mentally substitute the verbal definition of a symbol each time you read it, you'll get used to the symbol. All right? So that's what I do. Each time I say it, I say the verbal description. All right? Or the verbal definition. We denote the measurements of a quantitative data set as. The way we pronounce this is sub. This is a subscript. X sub 1, X sub 2, X sub 3. So if we go back and think about our ages, right, we could have had 44 as X sub 1 equals 44. X sub 2 was what? Right? X sub 2 was 57? No, 46. X sub 3 was 57. X sub 4 was 58. X sub 5 was 58. X sub 6 was 59. X sub 7, remember there was no 60 values, was 71. X sub 8 was 74. I think I skipped one. 43. Yeah, I skipped 43. So this is X sub 2. And X sub 10 was 85. So I could have wrote it this way, right? Notice I kind of had to pinch in that X sub 2. The nice thing about using subscripts is I can look at the highest value and know my end value. I know the size of this data set is 10. So this is just another name I could give it. X sub 1 was 44, X sub 2 was 43, and I say sub, X sub 1, because it's a subscript. An exponent, when the value is written up here as an exponent, you might hear that sometimes called as a superscript, right? So we call this a subscript, X sub 1. And you'll start saying that each time you read it. It'll become pretty natural once you do this enough, okay? We denote the measurements of a quantitative data set as X sub 1, X sub 2, X sub 3, dot, 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 X sub n. So X sub n is the last. In this case, the last one is X sub 10 for our ages problem, okay? Okay. Thus, if we have 5 measurements in a data set, we will write X sub 1, X sub 2, X sub 3, X sub 4, and X sub 5. If the actual numbers are 5, 3, 8, 5, and 4, we have this. Notice they're not written in ascending order here. It's kind of a nice thing to do. It's not necessary, all right, to write it in ascending order. You don't have to. If you can, I suggest doing it, but you don't have to. Most of the formulas we use require a summation of numbers. What is the root word of that? Sum, which means to add stuff together, okay? Most of the formulas we use require a summation of numbers. For example, one sum we'll need to obtain is the sum of all measurements in the data set, or X sub 1 plus X sub 2 plus X sub 3, all the way up to X sub n. Now you can imagine if your data set had 10,000 observations, doing this by hand isn't very practical, right? That's why we start off with really small data sets, okay? Thank goodness for computers to do that type of stuff for us, right? And you'll notice some of your data sets that you do in StatCrunch are pretty big, right? But it's nice that it's in a computer. To shorten the notation, we use the symbol capital sigma. Now, any of you that have ever been in Greek life, you probably recognize that symbol. That is a summation symbol. That means add together. Okay? The symbol sum, and then notice this n at the bottom for the summation. That is x sub 1 plus x sub 2 plus x sub 3 plus dot 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 all the way up to x sub n equals the sum of x sub i's when I goes from 1 to n. Now that's, yeah, so n has to be given to you, right? You have to know how big it is. In this case, n is 10. In that case, n is 5. In our miles per gallon example, n was 100. All right? So this means add together all the observations from the smallest one, x sub 1. Notice we don't start off with 0. We don't start off with x sub 0. We start off with 1. Okay? So for that case, we would say the sum of I equals 1 to 10 of the x sub i's equals x sub 1 plus x sub 2 plus x sub 3 plus 4 plus x sub 5. I'm going to run out of room here. Let me rewrite this a little bit smaller. So the sum of I equals 1 to 10 of the x sub i's equals x sub 1, x sub 2, so what I would do is I would go and replace my x sub 1 with the actual value. So the sum from I equals 1 to 10 of my x sub i's equals 43, or 44 plus 43. Notice that one's not necessarily in ascending order. Plus 46. Oh, not a comma. Plus 57, 58 twice. 59 plus 71, 74, and 85. All right. So all it would be is adding these values together. Now this had to deal with the age of people in whatever class it was, right? I said it was McDonald's at 9:30 in the morning. So if I wanted to know the average age, when I add all that stuff together, which we haven't quite got to yet, when I add all that together, what would I divide it by to get the average age of these people? This value that occurs on the top of the summation, right? N. Right? And we don't really deal with finding the average in this particular section. This section just deals with getting used to the notation. All right? So they did the 1 through 5. So let's go ahead and add these together. All right. Something I want to show you is how to use this in your calculator. So this is the TI-30X. If you have another TI, it's a similar operation. Crystal, I see you have a Casio, so it's a little bit different, but it can still do it.
No, I've got both.
Oh, do you?
Because I started off 106 with this, and I got the other one. I'm pretty sure that my daughter was played school with it.
Because I can show you how to do it on that. It's going to be a little bit different process. But, all right. So in this calculator, what you do is you hit this stat data button. Look at that thing that comes up. X sub 1. So what we do there is we put in our x sub 1. So I'm going to go ahead and use this data set. Okay? So I'm going to let 44 be x sub 1. 44. Press down on this directional button. And it wants to know the frequency. This is nice because you can put in if it appears more than once, which is something we're going to have to do for the number 58. Right? It appears twice. So there it is. There's my first observation. Then let's go down again. The reason that's there is from previous class. That's why these numbers are here. All right? So x sub 2 is 43. That appears once. X sub 3 is 46. That appears once. X sub 4 is 57. That appears once. Now, I could write 58 appears once and then do 58 appears once again. You can do it that way. But what I'm going to do is I'm going to let X sub 5 be 58. And I'm going to put my frequency at 2. So that means X sub 5 is 58 and X sub 6 is 58. So the next number that should come up is X sub 7, right? When I hit down on my calculator. Oh, and it didn't. This one doesn't interpret it exactly the same way. But let's keep going. So I'm going to call it 59. Appears once. 71. Appears once. 74 and 85. I'm going to go ahead and hit enter. Now, if that, if you don't like the subscripts changing, you can do 58 frequency 1, 58 frequency 1. That's perfectly fine. So now I've entered my data into the calculator. Now what I want you to do is hit this stat var button. Click that. Look what it tells me. It gives me an n value. It tells me the size of my data set, which is 10. In this case, I have 10 observations. This thing I haven't described yet, but that's the symbol for the average. All right? X bar. But what I want you to do is scroll over to the right. See how it has that little arrow? I want you to scroll all the way to the right. Look what it's got there. It's got sum of X. Sum of X. This sum of X and this sum of X are exactly the same thing. And when you guys manually did this in your calculator, is that the number you came up with? 595. Now, for a data set that only has 10 units, it's not too bad to actually do it by hand. All right? That's how we use it. That's where it's at. So this is a good way to check your homework. All right? Use this to check your homework. And I really want you guys to get used to entering your data in your calculator. And there are some other calculators that are nice because you can put multiple data sets in. Like the TI, I think it's a 31. Not sure exactly what the model is. But it'll let you it actually breaks your data sets into columns where you can put more than one. And you can see all your observations kind of on the same screen. If you have the big graphing calculator, it does it kind of the same way, the TI-89. Did you figure out how to use that one? Yeah? Okay. So that's our sum of X there. And that's not something I expect you to be an expert on right now after I've showed you in one example, all right? You really got to go home and try it on your own. And then you get a lot more comfortable with this notation. It's not just a bunch of gobbledygook, to quote another professor here on campus, right? Which is kind of what it looks like at first when you don't understand it. Now, another important calculation, because we need this in order to find what's called the standard deviation, is to add together the x squareds. And I really want to stress the difference between these two notations. Because it's something we have to know the difference between, because they both appear in the same formula. The sum from I equals 1 to 10 of our x sub i's squared is not equal to the sum from I equals 1 to 10 of our x sub i's squared. Those two things are very different. If you took 106, you've seen that a lot. This one is where we square the values and then add them together. This one is where we add the values together and then square it. All right? So I want you to notice that these two things are not the same. What does order of operations say? What comes first, parentheses or exponents? Parentheses. You always have to do the stuff in the parentheses first. Here there's no parentheses, so the first thing you have to do here, doesn't exponent come before addition? So in this case, you have to square it first and then add everything together, which is exactly what they're doing in this example. So on the previous page, for these 5 measurements, when they added them together, the sum was 25, right? Down here at the bottom. So the sum of the x sub i's squared would be 25 squared. What is 25 squared? 625. But look what they have on the other page. This one is the sum of the squares. Right? The sum of the squares. This is a lot different than 625. Very different, right? Extremely different. Especially with this example. I mean, the sum of all this was 595, right? So let's go back and look at the calculator and look at the differences. So let me go back to my stat bar. Notice this calculator does your sum of x squared right here. So it squares your x values and then adds them together. What's 595 squared? Huge number. 354,025. That's the sum of x squared. That's this value. Right? So the sum of our x's squared, so that's not equal to 595 squared, which is not equal to what? 354. So let's go look at what the sum of the squares was, not the square of the sum. So let's go back to the calculator. Over there, okay. Stat bar. Now let's go to the very right-hand one. 37,101 is the sum of the squared values, not the square of the summed values. All right? You kind of have to listen to that a few times. Sounds a little redundant, but it's not. This is the sum of the squares. This is the square of the sum. So this one equals 37,101, which is not equal to these. I mean, this is, man, that's like 10% of that, right? Extremely different. So imagine in your calculation, if somewhere you switch this number with that number or vice versa, you're going to be way off, right? You've got to really pay attention to that. Because in our shortcut standard deviation formula, you use both of these. Okay? Which we'll get to. Okay. What I want to do now, let's go look at your homework. Because your homework has some stuff I want you to come up with that we haven't done an example on yet. Because that's the end. Look, there's the end of it. So here's practice problems. This is the type of stuff you're going to have to do for your homework. So notice here, what this means is you take all the observations, you subtract one from them, and then you add them together. That's what that notation represents. That is not to be confused with the sum of x minus 1. So the sum, whoa, that's not a very good sum. That almost looks like a bracket. So the sum of x minus 1 is not equal to the sum of x minus 1. Do we see that? What's going on here? Because this means add them all together and then just subtract 1 from it. Because when you do order of operations, addition and subtraction are on the same line, right? So you always do it from left to right. So that means you'd have to do the sum of all your x sub i's and then subtract 1. This means you subtract 1 from each x and then add them together, right? So those are very different. It's because of the parentheses, right? Parentheses come first. All right, so let's go look at a homework problem. So let's go into 2.3. And you have to do 2.2 first. Where is that? Oh, that was 2.3, okay. So here we go. So you have to do 5 different observations. Notice the difference between B and E. They're not the same thing, right? One of them is where you add together the squares. E is where you square the sum. Right? Here on part D, that's not one we've done yet. Let's go ahead and do that example. Let's do that problem. Because you got plenty of practice in this homework assignment on this stuff. So here's my data set. So x sub 1 is 2, x sub 2 is 4, x sub 3 is 1. Notice these aren't in ascending order. X sub 4 is 3, and x sub 5 is 2. And if you click this box, it is where you can put it into a spreadsheet. You're welcome to play with this stuff. This is how the videos describe how to use this stuff, right? Section 2.2 has some videos that really explain what to do for each of these. Okay. So let's do part D. D says the sum from I equals 1 to 5 of x sub I minus 1 quantity squared. So this is equal to, let me do it right here. So it's x sub 1 minus 1 squared. Oh, yes.
2 minus 1 squared.
Right. Plus, yeah, and I'm going to do the subscripts, and then we'll actually put the values in. Yeah. And then x sub 2 minus 1 squared plus x sub 3 minus 1 squared plus x sub 4 minus 1 squared plus x sub 5 minus 1 squared. Sorry that got a little small right there. Now notice the parentheses do not include this, right? That's not what it's saying. Because that would mean you add together the x minus 1s and then square it. So you have to do parentheses, exponents, and then summation. So now, yeah, x sub 1 is 2, so this equals 2 minus 1 squared plus 4 minus 1 squared plus 1 minus 1 squared plus 3 minus 1 squared plus 2 minus 1 squared. So this equals 2 minus 1 is 1. So 1 squared plus 3 squared plus 0 squared plus 2 squared plus 1 squared. One squared is 1 plus, what's 3 squared? This. Nine. What's 0 squared? 0. When you have nothing and double it, you still have nothing, right? Plus 2 squared is 4. plus 1 squared is 1. So 1 plus 9 is 10, plus 4 is 14, plus 1 is 15. And that's your answer. There must be some kind of film on the bottom of this board. Notice how the marker kind of dissipates as you go to the bottom. And we'll have to do this type of stuff in the next section. It's just here we're going to replace this 1 with another symbol. Right? So part A just says sum of x. What is the sum of x there? 2 plus 4 is 6, plus 1 is 7, plus 3 is 10, plus 2 is 12. And have plenty of help over here. If you click this View an Example tab, it actually steps you through. Now, it's never the same data set. When you go to View an Example, it's always a different set of numbers. So don't go through this View an Example, come up with the sum of x, and then go put it in as the answer to your question. All right, you'll be wrong. Okay? But it's nice because it steps you through. Then you can expand that. So it was 18. And it says sum of x squared. So notice it squares the values and then adds them together. This is the one we just did, right? The sum of x minus 1 squared says, first find x minus 1 squared for each value in the data set, which is exactly what I did right here in this example, right? And then add them all together. Okay? Really, I definitely want to emphasize once again the difference between B and E. Now, there will be some cases where they're the same. Very, very few, but it could happen. It's not like they're never equal. Like, what if I just had one observation and it was 1? X sub 1 equals 1. Would those two things be the same? Yeah. So in that case, yes, they would both be the same. They'd both be 1. Okay? So lots of examples on that. Oh, let's click in here and kind of at least look at these. So there's 2 parts. Notice the parentheses squared. You need to add all that stuff together and square it and then divide by 5. All right, with that first part. Add it all together, square it, and then divide by 5. And this is nice because, look, it already gives you your sum of x squared is 43. Your sum of x quantity, your sum squared is 169. So it gives you those values. So what you can do is take that 43 and 169 and just replace it right there in part A. You guys see that? So sum of x squared is 43. So the answer to part A would be 43 minus, which I'm not going to solve it for you, 169 over 5. It says simplify, so that's not going to be right. Now, to simplify that, it wants you to get common denominators. So there's practice on fractions. All right? So let's go ahead and do that, because I know it's probably been a while since we've messed with that stuff. So let's go ahead and find that. So let's simplify that answer. And when you guys come in to do this problem again for your homework, the answer's always changed. It's dynamic, all right? Sorry. So all I'm worried about doing right here is simplifying 43 minus 169 over 5. Now, if in the parentheses it said round to 1 decimal place, you could just punch that in your calculator and hit enter. That's not what it says. It says simplify. It doesn't want a decimal. So what's the denominator on 43 right now? 1. What do I need to make the denominator look like? What do I multiply 1 by to get 5? 5. So whatever I do to the bottom, I have to do to the top. So this is equal to, what's 5 times 43? 165? 215. 215? Yeah, that's right. So it's 215 over 5 minus 169 over 5. What is that? 46 over 5. Now that can be rewritten as a mixed number. I don't like mixed numbers. All right? And I'll show you why. What is that as a mixed number? This is what's called an improper fraction, when the numerator is bigger than the denominator. How many times does 5 go into 46? 9 with a remainder of 1, right? So this is equal to 9 and 1/5. I don't like that because if I didn't have any context and I just had 9 and 1/5 written, I would interpret that as a multiplication. 9 times 1/5. But a mixed number, what that actually is an addition, right? That's 9 plus 1/5. So I don't like mixed numbers because there's not really any context to it right there. And when you get into any upper division stuff, we always leave our fractions in improper form, right? So I'm not saying you're wrong for writing it as a mixed number, but I don't know if this is equal to 9.2 or if it's equal to 9 times 1/5, which is 9 times 0.2, which is 1.8, right? Which one is it? It's 9.2, but if you don't really have any context, a lot of times when two values are written next to each other, it means multiplication. All right? So that's what I don't like using. I prefer the improper fraction 46/5. If you wrote 9 and 1/5 on a test, I wouldn't count it wrong. But it's just something to be aware of. Okay? All right. Same stuff here. Now pay attention to the negatives. The negatives do make a difference here. When you add a negative, you're really subtracting. Okay? So pay attention while you're doing that on your homework. And more of the same stuff. So lots of practice with this summation stuff. Okay? By the end of this, you'll be experts in it. All right? So, this assignment and 2.2, which I'm going to go and take a look at real quick. There's a prereq of section 2.1, of course. You have to get at least an 80 on it. The computer froze, it looks like. So notice here there's 3 videos. How to create a dot plot, a stem and leaf, and a histogram, which are the 3 graphs we created. This is Miss Moore, her videos showing you how to do it. Right? She's real good, goes through it step by step. And she really does a good job of not making his videos too long. Because that's not a good thing. Anything over 10 minutes, people tend to shut off. Right? When you see that little counter in the bottom right corner and it's like 7:52, people are a lot more apt to watch the whole thing. So this shows you how to do that. The 3 things that we did. Okay? And then 10 questions. So let's go look at due dates. So, today is the 3rd. Notice the participation agreement and the orientation of my stat lab were due last night at midnight. Or you can still do them for nothing off. Okay. Due tonight by midnight. So really the first assignments from the book is chapter 1 and section 2.1. Chapter 1 deals with all the definitions, right? A lot of words in there. Difference between quantitative and qualitative, descriptive versus inferential, all that type of stuff. 2.1 deals with graphing qualitative data. Bar chart, pie graphs, and Pareto diagrams. 2.2 deals with graphing quantitative data, which is the stuff we did today. Dot plots, stem and leaf, and histograms. 2.3 only deals with summation notation. And 2.4 is actually where we finally start to get into doing some statistics. We get into measures of central tendency, mean, median, and mode. And in order to find the mean, we use this summation notation, so that's why we had to talk about that first. All right? The mean is just sum of x over n. Right? That's the formula for the mean. The addition of all the observations divided by how many there are. All right? And then we move on. So, tomorrow is the last day this week, right? We'll cover 2.4 and 2.5. Now, I know we've kind of crunched a lot in the week, but as long as you take care of business during the week, then you notice you kind of have the weekend off, right? I've given you some time to relax. And then you get back into class and we go pretty hard, right, during the week. And I found that when you assign stuff during the week, students are just a little more apt to do it. I mean, when you get stuff done, you assign stuff on Sunday, and you only went to class last Thursday, stuff kind of slips your mind, life gets in the way, right? So, tomorrow we'll cover these two sections. That's why they're due 6-8, which is Monday. Then on Monday we'll do 2.6 and 2.7, which will be due next Tuesday. Next Tuesday we'll cover 2.8 and 2.9, which will be due next Wednesday. A week from today we'll review for the test, and then next Thursday we'll take our first exam. All right? Now, make sure you click this Show All button, and then View All on one page, because then it shows you the quiz. So this will be due next Thursday at test time. All right? And I think what I'm going to do, because it's not going to take an entire hour and 50 minutes, I'll have about a 15-minute question and answer session before the test. All right? So if you're reviewing, might have some questions about some stuff on the review. Because I found that to be pretty helpful, doing a review directly before. Not a big review, just a small review. Okay? And I haven't, and these are due the next week. Not quite, right? It'd be 11, 12, 13, 14, 15. Yeah, so that'll be due 16. We'll start that the Monday after next Thursday. All right, so we're in it. We're in the meat and potatoes. We're moving right along right here. This is the type of stuff you really need a good, concrete understanding in. If you have questions about any of this stuff, come and see me. Because as long as you really understand this stuff, then we start building on it, you don't get lost. If you don't understand this summation stuff, when we move on, that stuff becomes assumed knowledge. So then we get to problems where we use this stuff, and if you don't understand it, you can't do the problem. All right? Okay, guys? Any questions about anything? Remember, I have office hours right after class till 11:30, all right? Over in the JWLA, 211B. I'm usually in there longer than that, so. Okay? You're welcome to go start on your homework. You can go to the library or the UCC. Go log in and start, okay? All right, thank you, everyone. Have a good day. I'll see you tomorrow. Yes, sir.
Can you show me again
Yeah. Now how to put the data in?
Yeah.
So data is where you go to put the actual values in. So 43, go down, 44, 46.
See, I went in and I put frequency 2, but at the end it said that there was 11. There was 11.
Yeah.
It's because there's that one. Look, you have 84 in. You have 85 listed twice.
Yeah, it's
That's why.
interesting.
So you could go to here and delete that off. See, and then it's not. Yeah, it's just because you had 85 listed twice in there.
Oh.
See, this is only X sub 9, even though it was X sub 10, because you had that frequency 2.
Okay.
So then when you go back to the stat bar button, you look at tells you there's 10. You just had 85 listed twice, that's all.
And so you just went to like the first one you cleared? Is that how you got rid of it?
Yeah. No, I hit delete.
Oh,
Yeah.
okay.
So you could even go back and say, yeah, look what happened. So you go back to data, and maybe I don't want that in there. So I cleared it, and look, it automatically moved the previous one up.
Okay, cool.
So now if I go back to stat bar, we're going in.
Okay, cool.
All right. No problem.
Appreciate it.
Yep.
Is this the standard deviation right there?
No, I think it's SX. This is the variance. So
Oh, the variance.
yeah, so they're a little different.
Okay.
Yeah, and it's not exact.